Hello, good afternoon, everyone. I hope you're having a fantastic London summit so far. Just out of curiosity, how many people in the room are either experimenting with generative AI or actually have production workloads within the organization? Quick show of hands. Fantastic, great seeing so many hands up. Now, a second question. How many within the audience are training a large language model from scratch? So I can see a lot fewer hands up. And there might be very many reasons for this. One of the first is the power that the state-of-the-art generative AI models that have come out these days on services such as Bedrock bring to the technology community. Another, and maybe more topical for this presentation, is around the complexity and resources needed to actually train a large language model from scratch. My name is Simone Zucchet. I'm a senior solutions architect at AWS. And together with John Dupre from Thomson Reuters, we're going to cover when it might make sense to train your own model, the complications and challenges that come with training a model from scratch, and how Thomson Reuters leveraged SageMaker Hyperpod to train their own model, as well as the benefits it might bring you if you choose to embark on this journey. So the agenda for today, we'll quickly go through the generative AI landscape. We won't dive too deep into this, but just want to give a signpost to where SageMaker Hyperpod sits. Then we'll go through the challenges that training a large language model from scratch brings, as well as how SageMaker Hyperpod can help alleviate these challenges. And then John will take us through how Thomson Reuters has leveraged SageMaker Hyperpod in scaling their large language model research, a fantastic story that I'm pretty sure you'll all be excited to listen and learn from, to be honest. So let's go into the generative AI landscape. Now, generative AI has really changed the way in which we look at our workloads within organizations. It's been such a transformative, innovative technology, and it's helping to boost a lot of different innovative patterns within our organizations. Now, I don't want to dwell too much into what this does. There are many other presentations that will cover this. But at a high level, it is helping to boost employee productivity within our organizations. Generative AI is also helping to enhance our customer experiences with things such as interactive chatbots. And it's also helping to boost our internal business processes to make us more efficient and cost-effective. Now, in terms of how AWS can help, AWS views generative AI as a three-tier technology stack. At the top of this stack, we have applications that help you leverage the power of LLMs and generative AI without having to build your own workload. So it helps remove the undifferentiated heavy lifting of developing and running these by providing services such as Amazon Q for developers, Amazon Q Business, as well as Code Whisperer. And these help you within your organization leverage the benefits of generative AI. At the mid of this stack, in the middle of this stack, we have tools that you can leverage to add generative AI to your workloads. Bedrock is a fantastic example here, where with a simple API, you can integrate either existing services or brand new products within your organizations with generative AI capabilities. You can leverage Amazon's own first-party models or third-party models such as Llama 3, for example, that was recently announced. And then at the bottom of the stack, we have infrastructure that can help experts train and customize their own models. Now, this is where SageMaker Hyperpod sits. And it's designed to help specialized machine learning practitioners leverage our internal services, our infrastructure, and a lot of the work that we've done around software to be able to train models from scratch. Now, why would you want to customize a model? Why wouldn't you want to use a model out of the box? There are a few reasons, and many of these have to do with adding context that your organization might have on top of the very powerful state-of-the-art models that are already available. So things such as customizing to specific business contexts is one of the first ones of them. We also have the ability to adapt these large language models to specific language. If we look at the legal, tax, or healthcare domains, there might be languages used or sentences used or phrases that large language models just haven't seen enough of to be able to be performant at helping you out in those workloads. We also have the ability to enhance specific tasks. So there might be a specific task that your organization does that a model out of the box just can't do by itself, and you might need to customize it to perform better. And then lastly is context. I like to think about the current president of, let's say, the United States. If a model is trained based on data now, and in 2026 you ask who was the president in 2025, it might hallucinate, it probably will hallucinate, and give you the wrong answer. And that's just because it hasn't seen that data before. But if you have proprietary data that you want to include within your model for your particular workloads, then customizing a model is a great way to get more performance out of large language models. In terms of the common approaches of customizing foundation models, we do have a few. So on this graph that I'm going to show, pay attention to the y-axis. On the y-axis, we have quality increasing, but at the same time as that increasing, you have an increase in complexity, cost, and time needed to customize your model. One of the simplest and actually most powerful ways to customize a model is by using prompt engineering. In this, we iteratively and creatively mold the prompts that we ask the large language model in order to steer it in the direction in which we want it to respond to our prompts and questions. Next, both in terms of quality but also complexity, is using retrieval augmented generation. Now, what we do in this is we provide not only the prompt that we worked in prompt engineering before, but also relevant data and context. It's a fantastic way to get models working on either proprietary data or data that they might not have been trained on or exposed on. We then move to some of the more time-intensive and cost-intensive and complex ways of customizing models. You can customize an existing foundation model using proprietary data, which are specific to your domain, by either fine-tuning or pre-training. In this step, we provide data, and these help to update the model weights and allow the model to better solve your particular domain questions while keeping the ability to generalize. And the last, most complex, but also likely to give you great results if you have the right set of data, is training a foundation model from scratch. In this, you provide a lot of proprietary data, which are specific to the domain you want to train on, and you train the model from random initialized weights. The output of this will be a model that is specialized in your particular domain without any bias or inherent discrepancies introduced from other more general data. SageMaker Hyperpod helps you in this particular case by removing the undifferentiated heavy lifting that you might have to do in running both the infrastructure and training processes for training your data. But when does training a foundation model actually make sense from scratch? Now, I alluded to it earlier, but in most cases, prompt engineering, RAG workflows, or fine-tuning with the current state-of-the-art models is more than likely to be able to actually help you achieve your generative AI tasks. But if you have a workload in a very specific industry domain, such as legal or tax, or you have a specific workload that you've tested and it just doesn't work with all the other options of customization, and you have both the specialized machine learning practitioners and resources, then training a model from scratch might be a worthy endeavor. SageMaker Hyperpod is the AWS service that has been designed to help companies and organizations that have chosen to train their own large language model from scratch, and it helps them do that by removing that undifferentiated heavy lifting. If we look at how it allows you to do so, first, it provides a high-performant and resilient infrastructure and platform. It automatically heals when there are issues, and this alone helps to save in training times by up to 20%. We also provide streamlined distributed training, which once again will help you take advantage of all your resources and additionally help reduce training times by up to 20% and performance as well. And then lastly, we also provide mechanisms that help you use these resources a lot better, helping you reduce the amount of time you need to actually develop the platforms in training a large language model from scratch. So let's look at some of those challenges. We've seen the benefits, but what are the actual challenges in training your own model? The first and maybe most important challenge is just the amount of compute needed to train your own model. In this graph here, we have on the y-axis the amount of compute needed to train a model in petaflops. And on the x-axis, we can see over the last few years the amount of resources needed to train a model. Now, for me, what was shocking the first time I saw this is that scale on the y-axis, that's in a logarithmic scale. So that grows exponentially and has grown from 10,000 all the way to 10 million petaflops over a short period of time. This increase in compute means you need more instances in your clusters. It means you need to network them better. And all these clusters need to talk to each other and provide data to each other. And that just increases with the amount of, and the complexity of that increases with the number of clusters you have. Next, having the infrastructure isn't everything. You also need to be able to actually leverage that infrastructure. And the software becomes a massive burden as well for many development teams. The reason for this is because of the massive size of data that you're using to train, but also the massive size of models. Organizations need to split this data into chunks and then load them into all the different instances. Now, this is a lot of work because not only do you need to manage this, but you also need to tune this for the different model architectures, the type of data you have, and even the architecture. So developers have to spend a lot of time creating the right code to be able to run this, and then iterate it continuously as you continue updating your models and continue your training runs. And then lastly, having the right software and having the right hardware, that's not it. It's also bringing it together that becomes highly critical. You need a stable platform that is able to last for the duration of your entire workload. Why that's important is these training runs are tightly coupled. Every training run within your architecture will be sharing data across all the different nodes, and this is a highly serialized process. If you lose one node, that can knock out the rest of your training run. You then need to figure out ways of saving your progress, much like you would maybe back in the day with old games. If you didn't save and you lost power or a naughty sibling pulled out the power cable, you'd lose all the data and all the progress you made from that day's worth of gaming. Very similar with machine learning and training large language models, only the consequences are a lot bigger. Hyperpod automatically handles a lot of this for you, be that optimizing how you deploy your data and models on the different workloads, as well as providing checkpoints that can be automatically retrieved when an instance fails. And SageMaker Hyperpod also actually helps you to replace these instances for you. Now, I've alluded into some of the benefits of SageMaker Hyperpod, but we're going to cover them in this section here. So SageMaker Hyperpod's characteristics focuses on three main components. The first is the performance, using the most performant networking, compute, and storage possible to allow you to be able to train your models as quickly and as cheaply as possible. Next, we have resilience. So what happens when an instance fails? Or what happens when you have a software error that causes an issue with your training run? Well, SageMaker Hyperpod helps when it comes to resilience as well. And then lastly, there's ease of use by the use of managed frameworks and libraries, allowing you and your developers to be able to run these workloads a lot simpler than you would if you had to start from scratch. And now we're going to dive into these one by one. So first is the cluster creation process. Now, this is actually a very simple process when leveraging SageMaker Hyperpod. I'll take you through it now. The first step is actually organizing your own data networking so that you can provide data to the model as it's being trained, and so that your machine learning practitioners and engineers are able to actually use the nodes within your SageMaker Hyperpod clusters. Next, you create a lifecycle script. Now, what a lifecycle script is a series of scripts that run when you're provisioning your different nodes. This allows you to customize those nodes to best fit your training runs. So if you have any specialized code, or if you want to run any additional logging mechanisms, however you want to customize your nodes, you can do that with a lifecycle script. The next thing you do is you create a configuration file. Now, what this configuration file does is it specifies what your actual cluster on SageMaker Hyperpod would be. So I've taken a quick snippet of one of these being created, but you can do things such as specify the instances that you want to run, both on the compute side and on the head node. You can specify the lifecycle scripts that you want it to run, or the versions that you want to run, and also the number of instances that you want in each of those parameters. Once you've provided all of this, you then hit the simple create API that starts the deployment for you. It handles all of this automatically for you. And once the cluster is created and ready, your users can then log into the head node and start training jobs. And they can do this by SSH, or even also via Systems Manager as well. In terms of an architecture of what that looks like, here we have the AWS cloud. We have your resources that you create for storage and networking. You then hit the SageMaker Hyperpod endpoint with your lifecycle script and configuration file, and that automatically deploys your cluster for you. Your users are then able to SSH in this example and start deploying workloads on the cluster for you. Now, we talked about how your users would be able to deploy workloads, but how is that actually done? So SageMaker Hyperpod provides a managed instance of Slurm, and that is basically there to help you manage how your resources are leveraged on the clusters. By using Slurm, the scheduler is able to help you work on different types of workloads, both in parallel or sometimes in series. The type of workloads machine learning practitioners can run on SageMaker Hyperpod include using SBatch for long-running training jobs. These can last multiple weeks and use tens, hundreds, maybe even thousands of instances. You can also reserve instances as a prototyping team. So a machine learning practitioner can ask for 4 instances and quickly iterate on small training runs to be able to prototype. And then lastly, SageMaker Hyperpod also makes it very easy for you to use third-party schedulers and frameworks and tools to be able to actually run your workloads. So you're not limited to Slurm if that isn't what you want to be using. Now, in this case here, you can use third-party tools like Mosaic Composer, Array, really anything that you'd want to install and interface with. Hyperpod makes it very easy for you to do so. In terms of how Slurm works in a practical sense, here we can see that an admin has created a Hyperpod cluster with 16 instances. We have user A who wants to run a long-running training job, and Slurm automatically distributes this across the instances needed to run the job. Next, we have another user who wants to run an experiment. And because we have the availability, Slurm is able to actually leverage those 4 instances for that experiment. User C might come on and want to use a specialized framework or third-party tool. And again, Slurm is able to automatically provide those resources without any input from an admin. But what happens if user D comes in with a workload? Slurm allows you to give prioritization to workloads. So if this workload had a higher priority than, let's say, the experimentation, it's able to switch out those workloads for you and resume after. It is also able to simply queue if all the running jobs are of the same priority, and then start that training once the other jobs have finished. Another great, and I think it's actually one of my favorite features when it comes to Hyperpod, is the resiliency. So imagine if you're a machine learning team or practitioner, you've used 16 P4D instances to train a large language model on this training run, and it's been running for, let's say, 28 days. What would you do if an instance failed and your whole training run collapsed? Would you be able to recover? Or would you panic? Well, failures can happen for a whole host of reasons. It could be hardware related, or it could be somewhere in the software. But the result is often the same. What ends up happening is one instance will have a failure, and this has a chain reaction and knock-on effect that can lead to the loss of an entire training job. Now, if this happens, there'll be idle capacity as you're frantically trying to troubleshoot those issues. And then you'll have to have a lot of time as you're debugging and restarting. Hopefully, you've saved progress as part of checkpoints, but if you haven't, then that means losing the entire job process and starting again. The automated recovery that SageMaker Hyperpod brings helps make this a worry of the past. So with SageMaker Hyperpod, the service runs agents for you on your instances within the cluster, and these automatically monitor your health of the instances. If they detect a failure, they will automatically go through a built-in troubleshooting process that identifies the issue, where that issue stemmed from, and will replace that instance for you. By the usage of checkpoints as well, it will automatically kickstart the training process from your last successful run, allowing you to not have to manually come and intervene within the process. Checkpointing is one of the most important parts of the job healing process. So with checkpointing, SageMaker automatically saves progress from X amount of training runs. Now that period can be configured by you as a user. If it detects a problem with the training, it will replace the instance and recover using the previous steps that I showed. What it will then do is go and look for the last successful saved checkpoint and kickstart your training again from there. This is the simple code that SageMaker Hyperpod uses. On the left-hand side, we can see that the first step in actually running your training job is checking for if there's a checkpoint and using that. And if it isn't, you've started training from scratch, so it doesn't need to load it. But how does this look from a practical point of view? This is a loss plot showing the training of a model. In blue, we can see where SageMaker Hyperpod briefly pauses to take your checkpoints. In red, we inject an error, and this causes a collapse of the training job. But rather than having to start again or a long process of training, the green shows where SageMaker Hyperpod automatically recovers and restarts the training process. Now imagine how long this would be if you had to log in at 3 a.m., troubleshoot the process, fix it, and start it again. Or even worse, if you didn't have a checkpoint and you had to start from scratch every single time you had a failure. Those are some of the key benefits, but there are the optimizations throughout the stack. From an infrastructure perspective, SageMaker Hyperpod leverages the latest generation of EC2 Ultra clusters. You can run P4Ds, P5Ds, or Trainium instances that bring you that high level of high-performance compute to your clusters. You also have advanced networking with Elastic Fabric adapter. And when it comes to storage options, you can use FSX for cluster and S3 to make it a very performant, high-performance compute infrastructure. From a software perspective, you have managed libraries such as SageMaker's data distributed parallel or distributed data parallel libraries, the Amazon S3 connector for PyTorch, and you can also customize your instances by using containers or lifecycle scripts. When it comes to observability as well, you have the SageMaker suite of observability. You can use a CloudWatch as well, or install any observability tools that your team might want to leverage. So that was a whistle-stop tour of SageMaker Hyperpod and where it might be useful. I'd now like to hand over to John to tell us about how Thomson Reuters leveraged SageMaker Hyperpod in scaling their large language model research and training.
All right. Thank you, Simone, for that excellent overview. This will be a lot easier without those on. Excellent overview of SageMaker Hyperpod. Hello, everyone. My name is John Dupre. I'm a distinguished engineer for Thomson Reuters Labs. I'm going to tell you about Thomson Reuters' generative AI journey, where one of the things we're exploring is training our own large language models. We were challenged by the computational scale of the problem, and through close partnership with AWS, we were able to use a pre-GA version of Hyperpod to be able to address that challenge. So, in my opinion, 2023 was the year for generative AI with the release of a number of groundbreaking large language models by third parties. I think in retrospect, the lead up to this point is obvious, but the speed and impact at which it hit in 2023 was undeniably transformative to the business landscape. Now, every business that deals with information is working diligently to figure out how to make use of this technology. So LLMs are great, but with any technology, learning how to use it effectively is critical, and LLMs are no exception. Every business must understand that LLMs do not model language or knowledge with 100% accuracy. They've been known to hallucinate or confabulate, sometimes comically, and sometimes in brand-damaging ways. And depending on your business, publicly available LLMs trained on the knowledge of the internet may not be sufficient for your use cases. Additionally, public LLMs may not meet your speed needs, address your cost concerns, or your capacity requirements. Now let me tell you a little bit about our business, Thomson Reuters. We serve legal, tax and accounting, risk and fraud, and global trade professionals. Our news and media is globally recognized and helps make sense of our world around us. Our customers have very specific information needs, and Thomson Reuters has world-class content and subject matter expertise in these fields. And we work diligently to clarify the complex for our customers. Now, if all that sounds a little too abstract for you, consider just one of our customers, the US trial lawyer. The US legal system is based on precedent. That is, the outcomes of past trials can influence the decisions of future trials. What this means for a trial lawyer is that they must thoroughly research past cases and be prepared to argue for how they do or do not apply to the case, their case. With over 200 years of precedent, 7+ million cases, exhaustively researching their case is challenging and time-consuming. Their research must be complete, and there is zero tolerance for inaccuracies. Thomson Reuters products should not misrepresent the facts. They should not hallucinate or confabulate. Now, at the same time that Thomson Reuters is looking to leverage generative AI technology, our customers themselves are trying to make sense of how this technology changes the way they work. This is a journey that we share with our customers, and we have a plan. First, you should know that we're no stranger to AI. We just recently celebrated 30 years of AI in our products, starting with our natural language search engine in the 1990s. And we're well positioned to usher in generative AI today. We have an increased focus on our AI strategy with an additional $100 million invested per year. And we have a buy, build, and partner-based approach. On the buy side, we purchased Casetext CoCounsel and SurePrep last year. In the year prior, we purchased ThoughtTrace. And all of these add to our AI portfolio. On the partner side, Thomson Reuters Ventures is working actively to find strategic partnerships and investment opportunities in AI startups. But we're also working to innovate by building as well. GPT-4 dropped in 2023, and Thomson Reuters quickly launched into creating generative AI solutions based on retrieval augmented generation. We released generative AI capabilities in our flagship products, starting with Westlaw's AI-assisted research in November of 2023, and we followed up quickly in January of this year with our Practical Law product, and many more are on the way. Now, while we were working on those near-term RAG-based solutions, Thomson Reuters Foundational Research started work on exploring training our own large language models. And that's largely what the rest of my talk here is about, in particular around how we scaled it using SageMaker Hyperpod. So our research had two fundamental questions that we were looking to answer. Three fundamental questions. Can Thomson Reuters editorial created, curated, or enhanced data be used to improve LLM knowledge for a specific business task? Would smaller LLMs trained on Thomson Reuters data perform on par with very large LLMs? And perhaps most importantly, what methods could we employ to train the domain-specific models to get the best results? The benefits as we see it fall along three pillars: quality, agency, and efficiency. It's possible we could tune LLM generation to our domain and integrate more tightly with our RAG solutions. This would directly impact quality. And if we own the models, we control when we train them and how we train them, and we can tune the behavior that we want. And lastly, if we can train smaller domain-adapted models, they're likely to run faster, be cheaper to run, scale better, and reduce the overall cost. Our experimentation would focus around how well do open source foundational models perform on specific tasks, And does performance improve when augmented with Thomson Reuters data and applied to Thomson Reuters tasks? The tasks we would focus on were legal summarization, classification, and question answering. And the data we would use would be publicly available general textual data and legal data from primary and secondary law. Primary law would be content published by the courts and enhanced by Thomson Reuters editorial process or annotation processes. And secondary law would be Thomson Reuters subject matter expertise and analysis and annotation of the law. We would focus on continuous pre-training and instruction fine-tuning. For continuous pre-training, this would be an exercise in finding the right balance between the domain-specific data and the general textual data. And for instruction fine-tuning, to tune to specific Thomson Reuters tasks, this would be an exercise in generating instructions from Thomson Reuters data using various techniques. We would train against open source foundational models, and we would compare to industry standards like GPT-4. We would use automatic measures Perplexity and Rouge to help us determine how well we were doing in those two areas. In short, experimentation was going to require a lot of training. To get a feel for just how much it would take to train, we used the Chinchilla scale, which gives us an idea of how much training tokens are required for a given model size. This scaling law is published research that found that the model size to the number of training input tokens scales proportionally. And we used other open data to help us determine how long it would take to train a particular model given a number of GPUs. So for example, if we wanted to train a 7 billion parameter model, it would take about 132 billion training tokens. And if we use just 8 P4Ds, it would take about 7 days for that training to complete. And we quickly found that GPU resources are in very high demand. It was virtually impossible to get one P4D, let alone the 8 or 16 or 32 that we would need to do the work. We know because we tried for over a month to get just one P4D and failed. Normal capacity reservations were equally unreliable. And we did look at third-party options that promised to provide scale, but for various reasons, including our own data security concerns, they just didn't meet the needs. So we looked to AWS, a trusted partner. They introduced us to Hyperpod, which was not yet available, but they were willing to make it available to us in a preview form. With Hyperpod, the customer provides the capacity they need over time, and Hyperpod provides that capacity, ensuring that the network is healthy and resilient. And the table shown here is the capacity plan that Thomson Reuters used over the course of about 5 or 6 months. I'd like to focus briefly on just one aspect of the preview version of Hyperpod because it impacted our adoption of it. GA customers won't have this concern, but this was part of our journey. Hyperpod residency is split into two parts. The control plane resides in the customer's account, and the worker nodes reside in the AWS account. And they're connected through cross-account VPC peering. Now, with any pre-release software, there are going to be some challenges, understandably, because it's not fully developed. For Thomson Reuters, the VPC peering was a challenge for us. It just wasn't a standard that Thomson Reuters security was comfortable with. They would have preferred connectivity through AWS Private Link or Transit Gateway. But we worked with AWS and our security team to mitigate these challenges across 3 pillars. Under isolation and controlled connectivity, we created a dedicated AWS account and VPC, along with stringent security groups and network access control lists to ensure that we had a tightly controlled environment. And under private networking, we ensured that everything was on the private subnet and that there was 0 internet access except for initial setup and during maintenance windows. We also ensured that the data transferred over the VPC peering went over Amazon's private backbone network. Lastly, we ensured the data was encrypted at rest and in transit. And we had a policy to completely tear down the worker nodes to ensure that any residual data was removed before those nodes got recycled to other customers. The resulting account structure is shown here. On the left-hand side is Thomson Reuters' permissive research account. And this is where we staged the data for training. We would chunk it and tokenize it, and then we would transfer the training tokens over to the control plane where we would submit our training jobs. So, with the mitigations in place, we were finally off the ground and training our LLMs with Hyperpod. Over the course of about 5 months, we ran 20 training jobs, and we scaled our cluster up to 16 P4D. The largest job we ran consumed that entire cluster. It was a 7 billion parameter model trained on with 400 billion input tokens and took about 36 days to complete. And I think the most amazing part about this is that there were 0 hardware failures. So, how did we do? Well, things are looking pretty good with our training. Preliminary results for our continuous pre-training is that we were able to introduce domain-specific knowledge into the model while also retaining the general knowledge of the foundational model. We used a measure called perplexity, which basically indicates how confident the model is in its predictions. A lower perplexity indicates a stronger or more confidence the model is in the predictions. So you can see on the bottom half of this graph, our domain-specific perplexity went down. That's a good thing. It means it learned, it was confident in the generations for the domain-specific language. And on the top part of the graph, you can see that perplexity went up a little bit initially, but quickly leveled off. This experimentation was largely about finding that right mix of general training data with our domain-specific data. Likewise, for instruction fine-tuning, experimentation showed that we were headed in the right direction. We used a measure called Rouge to determine how well our domain-adapted models were performing against GPT-4 for those specific Thomson Reuters tasks that we mentioned. This automatic measure is based on term overlap. It's not the same as human preference judgment, but as an automatic measure, it gives us a decent indication of directionally which way we're headed. So for summarization, you can see that for our small 7 billion parameter model, as we added instruction fine-tune collections, we performed on par or better than GPT-4. On the other hand, if you look at legal classification, even for our larger 30B model, we did not reach GPT-4 level of quality. So clearly more experimentation is required here, though directionally you can see that as we added more instructions, we did improve and start to approach GPT-4 level of quality. Now you might remember there was a third task, legal question answering. The results there are too preliminary today to report. So that's our journey to date. Very promising results. Where do we go from here? Well, we want to explore training with larger foundational models like Mixtral 8x7b and Llama 270b. And we want to explore using direct preference optimization for a fine-tuning technique. In the past, we had used reinforcement learning from human feedback. Closing thoughts. So in conclusion, Hyperpod works as advertised. While VPC peering was a sticking point for us, GA customers won't have this concern at all. And for us, because we were experimenting, we were a bit challenged by capacity planning because our future capacity needs are often determined by whatever the results of the current experiment or training job run was. So as a consequence, we often kept our cluster larger in size than was needed just to ensure we had enough capacity for the next round of training that we wanted to do. Now, we offset the cost of that somewhat through AWS savings plan agreements that we had. So, does SageMaker Hyperpod make sense for you and your business? Well, I think the first question you should ask is, does it make sense to train your own LLMs? and think back on some of the reasons why we thought it might make sense for us around quality and agency and operational efficiency. If your business works in deep verticals with domain-specific knowledge that isn't available on the internet, or you have very specific domain tasks that you want to accomplish, training your own large language models could very well make sense. You'll have to weigh the cost of training your own models and keeping up with the rapidly evolving LLM technology. Now, if you do decide that training your own LLMs makes sense, then you're going to need a significant amount of computational capacity to do that, and SageMaker Hyperpod can provide that capacity, ensuring the health and resiliency of those nodes. Other things you might want to consider is EC2 capacity blocks for ML. These are good for smaller training jobs that are probably shorter running. And you might also want to consider the Trainium instance type. Anecdotally, we found that Trainium seems to be more available on demand than, say, P4s or P5s. That's our story. Last, I just want to say thank you to AWS. Without them, we would not have gotten as far or as fast as we did with our LLM experimentation. They really went above and beyond to ensure our success. So thank you, AWS.
Thank you very much, John. Having lived through this experience with Thomson Reuters, I really think that they are innovating and at the bleeding edge of model research. I really look forward to see where the next steps take us and to be able to show off even more interesting data and successful model trainings from the team. We don't want to just end it there. We want to give you the ability to learn a bit more and dive a bit deeper into how you can either use generative AI or train your own models from scratch if that's a worthy endeavor for your business. So we've provided a few hyperlinks. These will take you to both AWS and Thomson Reuters websites. Here you'll find a bit more blogs and posts and instructions on how you can use the different services we talked about today. We're also working on a blog that describes what we did here, so we'll dive into that in the coming weeks and months. Another thing I wanted to say is that the Skills Builder is a fantastic place, not only for learning about generative AI, but also to learn more about how to leverage the AWS cloud. So if you can or if you haven't yet, please do register and have a play around. Fantastic learning material on that website. And then lastly, I'd like to thank everyone in the audience for joining. I'd love it if everyone could quickly take a picture of the QR code and help provide feedback. That can help John and I in knowing what we did well and how we can improve, but it also gives us better feedback on how to put on better shows for the next sessions. And then lastly, if you have any questions, John and I will be to the side, so feel free to come up and talk to us. But we've also added some of our contact details there, so feel free to come, ask questions. We'll be more than happy to dive into some of the details we couldn't speak about because of the 45-minute time slot that we had. So thank you very much, everyone, and hope you have a great rest of the summit.